Hello everyone, this is Devasatam and you're watching the fifth lecture of EE635 Applied Linear Algebra. This happens to be the first module. Okay, so quick recap of what we have done in the last lecture. In the last lecture we saw, we broke the shackles of all these, what should I say, specificities of things like, kind of doing things only over real numbers, yeah, or columns of numbers, these sort of things. And we saw that we can expand to situations where the numbers are not necessarily just real numbers, but instead could be coming from any field. So field, we came to know that field is a special kind of structure of a set which allows us to do addition, subtraction, multiplication, and division, all these four basic arithmetic processes. Okay, then we saw that not just this level of abstraction, not just that we can deal with more exotic kind of numbers other than just real numbers, but we can also do things for situations where they are not just columns of numbers as vectors. Yeah, so we saw a much more general abstract definition of what is known as a vector space. Yeah, so it would be a good point for you to go back and see the definition of a vector space, where we saw there are these various axioms which define a set as a vector space. So a quick recap of that definition is that a vector space essentially is a set called V. The elements of them of that set would be called vectors, together with a field, elements of which would be called scalars. And with these two things, the vectors would allow vector addition. That means you pick two elements from that vector space, two vectors, you sum them up. There is an operation called summing of vectors called vector addition. You pick two and then sum them up. The result that you get is also an element from the vector space, right? And you pick a vector from the vector space and a scalar from the field, and you can multiply them, called the scalar multiplication. And this result also is an element from the vector space. Now, this addition and multiplication, of course, have some properties that they have to satisfy. Like the addition has to be commutative, associative. There should be an additive identity. There should be an additive inverse for every element. Yeah. Similarly, scalar multiplication should be, so it should have some sort of an associativity. And there are these two properties for distributivity of the scalar multiplication over the vector addition or the addition in the field. And then finally, one more point about the multiplication, that the multiplicative identity in the field, that is the one, that one when it multiplies to a vector should give me back the vector. Right? So these are the properties that defines a vector space. Now, with those vector spaces, we learned two very important ideas. First of all, before we go to these ideas, we also looked at various examples of such vector spaces, which are not necessarily columns of numbers only. Of course, columns of numbers do form a set, which is obviously a vector space, because that is what this idea of vector space is actually built on. But more than that, you can now think of matrices as vectors. You can think of functions as vectors. You can think of random variables as vectors. Yeah, there are these all sorts of things that you can view as vectors now. Okay, and then we learned two very important ideas about vector spaces. Namely, the first one was the idea of a subspace, which is a subset of a vector space, but also is a vector space in its own right, with the same operations, that is addition, vector addition and scalar multiplication, that were there for the vector space, for the parent vector space. Okay, and secondly, we also learned this idea of what is known as the span of a given set of vectors in a vector space, right? And then we learned that the idea of span is nothing but the idea of span. So, okay, the definition of the idea of span is the following: that if there is a collection of vectors called the set S, and then if you look at all possible linear combinations of S, of vectors in S, and collect them together. What you get is a subspace, first thing, and secondly, it also, this is called the span of that of S. Now, together with that span, this idea of span, this definition, we also found out that span is nothing but the intersection of all those subspaces that contain the set S. And that way, the span happens to be the smallest possible subspace that contains the set S. Okay. Now, yeah. So that's about it. Let us move on with what with some more ideas about this vector space, which will be very crucial for us to proceed. And before that, I have to share my screen. I hope it should be up any moment. Yeah, there you are. Okay, so, right. So as I said, span of a given set S, which is a subset of V. So first thing, now we are always going to say, unless otherwise specified, we are always going to have V as a vector space. Vector space over the scalars of field F. And that's going to remain almost fixed unless we specify it otherwise. So span of S, where S is a subset, it's not a subspace to start with, subset of V is defined as, so we write it like this, span of S, which we also define as S. This happens to be the collection of all summations like alpha I, I going from 1 to n, where S1, S2, dot, 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 up to Sn are elements from the set S, and alpha 1, alpha 2, dot, 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 up to alpha n are elements from the field. So this is typical linear combination. Okay, right. So this is the span, and we found out there was a theorem which said that consider the family F, which happens to be the collection of all W's which are subspaces of V, such that S is a subset of W. Then span of S is in fact equal to intersection of all the W's over the set F, over the family F. So look at all possible subspaces that contain the set S as a subset, and then the intersection of them will be equal to the span. Now note that in this situation, we never restrict ourselves. I mean, we don't have to restrict ourselves to set S which are finite. S could be an infinite set also. But remember that when we are talking about this linear combination, yeah, that the collection of all possible linear combinations, such linear combinations are defined only as finite sums. We can never talk about sums of, infinite sums of vectors. Those are infinite series, and we would have to do a lot of extra. We would need a lot of extra machinery to actually make sense of infinite series, which we don't have at this point. At this point of the course, we have not seen anything like that. We are not discounting it completely, as if time permits, we'll see it later on if we have the time. But now, for the time being, remember that linear combination would mean finite linear combinations, although the set S can be infinite. Let me give you an example so that to put things into perspective, so that it will be easier for you to understand. So, for example, our favorite vector space here, the two-dimensional Euclidean space R2. Yeah, okay. So now in R2, suppose I have this point, which would correspond to this vector, right? Now, what is the span of this vector? So let me call this vector as V. So the question is, what is span of V? So look at all possible linear combinations. So multiply this by 0, you get this one. Multiply by this by any other scalar, you get something here, here, something here. In fact, you get all possible vectors that lie on this line. So this is the line, this is the space spanned by the vector V. So this happens to be the span. And indeed, you can check that if you have just this point, which was our initial point, the smallest possible subspace that will contain this one, contain this vector V, is of course this line, the line that contains this vector V, right? So that way, this indeed is the smallest possible subspace, or rather the intersection of all the subspaces that contain the vector V. Yeah, but this is just a single vector. If I have two vectors, let's say in the same vector space, suppose now I have this vector and this vector. So 2 points, 2 vectors. So namely, let's say V and W. So I want to find out VW, span of VW. What is that? Right? What is the smallest subspace that contains both of them? In fact, the entire space. All of R2 happens to be the span. Because all of R2 is the span. So in other words, VW is nothing but all of R2. And in fact, you can in fact check that every other vector can be written as a linear combination of V and W. So therefore, by taking different linear combinations of V and W, I will get every possible vectors in R2. Yeah, so therefore, the span is indeed a whole space. What if I have an infinite set like this, for example? Suppose once again I am in R2. Now suppose I have, say, this the collection of all the points in this line segment for my set S. So this is my set S. What is S? The span of S? What would it be here? What is your guess? What is the smallest subspace that will contain everything in S? It of course is this line. That's the span. You may ask once again the question that what are all the possible linear combinations of vectors from S? You'll get back the same thing. So that's the beauty, that's the power of the result that we proved in the last lecture about the connection between the span of a set and the description of the span as the smallest possible subspace containing that set S. Yeah. As an immediate attention problem to you, why don't you think and find out in R2, suppose this is my set S. Yeah. What is the span of S? That is your immediate attention problem. Think about it. Similarly, also think about the situation over higher dimensions. Yeah, we are in R3. In R3, suppose I have this set. I have this set. This is S, which lies in the, say, x1, x2 plane. Yeah. What is, this is your another immediate attention problem. Okay. Now, once we did this, we also looked at two very important concepts concerning subspaces, namely intersection of subspaces, W1 intersection W2, and we saw that intersection of subspaces is always a subspace. It's by default a subspace. However, union of two subspaces is not in general a subspace, but one can look at the span of union of That happens to be what is called W1 plus W2. This separately is defined as the collection of all vector sums of this form, where W1 is coming from this subspace W1 and W2 is coming from subspace W2, right? Yeah, so that's about it. That's what we did in the last lecture. As I said, in this lecture, we're going to see some more very important concepts. We'll start with two very important concepts in this module. What is that? First one is the idea of linear independence. We have already seen some sort of, I mentioned in passing the word linear dependence quite often, but now we're going to formally define it. And once again, remember that we are not confining ourselves to just finite sets. We will talk about infinite sets in general, unless we mention it otherwise, unless we say that this is indeed a finite set. So once again, so this will come to you as a definition. Definition of linear. Okay. In the same definition, we'll define both concepts, dependence and linear and independence. So that's why I'm writing it this way. Okay. Now, what is the idea? How do we define this linear independence? So say, let S be a subset of V, where once again the standing assumption is that V is a vector space over a field F. So let S be a subset. Be a subset, possibly infinite. Okay. S is said to be dependent, remember, dependent or linearly dependent. Should I write this? Perhaps it is better to write it this way. Is said to be linearly, let me write it this way, dependent if there exists distinct, remember this is important, distinct vectors S1 dot 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 up to Sn in the set S and scalars alpha 1 dot 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 up to alpha n, of course from the field. Remember, this is important, not all equal to 0, such that the linear combination alpha 1 S1 plus dot 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 up to alpha n Sn is equal to 0. We will be calling this thing, such a linear combination, as such a linear combination as a non-trivial linear combination. Why non-trivial? Trivial linear combination means that every coefficient is 0. That means every vector is kind of multiplied with 0 and then added, which is like nothing. You're adding 0 vector with itself. But that's not the case. We are saying that at least one of these alpha i's is non-zero, which means this is a non-trivial linear combination. This is a term. Remember this term, non-trivial linear combination, because we'd be using this non-trivial linear combination word very often in this course. Non-trivial linear combination. So in words, what we are saying is that a set S is called linearly dependent if it contains a collection of distinct vectors which are such that their non-trivial linear combination, at least one non-trivial linear combination, is equal to 0. Then they're called linearly dependent. Of course, if a set, once again, possibly infinite, if a set S is not dependent, then, well, surprise, it is called linearly independent. Big deal. But wait, we need to see this carefully. What do I mean by not dependent? What does this mean? This means, so notice carefully, this is logically very important. I'm saying for a set S, if it contains some collection of vectors, which is whose non-trivial linear combination goes to 0, then it's dependent. I'm saying if it is not dependent, that means what? That means you will not be able to find any finite collection of distinct vectors whose linear combination would go to, whose non-trivial linear combination would go to 0. Then and only then it would be called an independent set. Listen, that for dependence, existence of one such collection S1 up to Sn was enough. But for independence, you have to check for all possible such S1 up to Sn's. Yeah, and then you'll have to conclude whether their linear combinations are going to 0 or not. Because you may pick some distinct vectors and you see that, okay, the linear combination does not go to 0. Does that mean it's independent? No, not yet. I have to check for more. I have to check for other S1 up to Sn's. Yeah, and none of them should give us a non-trivial linear combination that goes to 0. Then and only then we will be able to call that set as linearly independent, right? So around this definition, let me make some observations which will make this idea even clearer. So let's make some observations, yeah, which immediately follow from the definition. Number one, if S contains a dependent, okay, let me write this, contains a subset that is linearly dependent, and then of course S2 is linearly dependent, right? It immediately follows from the definition. If S contains a subset which is dependent, so that means that contains some vectors whose non-trivial linear combination goes to 0. Yeah, so that is contained in the bigger set also, in the set S. Of course, S is also linearly dependent. So whenever there is a set that contains a linearly dependent set, that bigger set also automatically becomes, by definition, from definition immediately it follows that that also is linearly dependent. Next is, if the 0 vector is a part of the set S, then S has to be linearly dependent. Let me write LD for linear dependence. Huh? Okay, so let me mention that here also so that there is no confusion. This is, LD is the shorthand I'm using for the phrase linearly dependent. So if S contains 0 vector, yeah, then 0 already is 0. So the non-trivial combination could be 1 times 0, that is 0. Yeah, that's the non-trivial linear combination that goes to 0. So any collection that contains the 0 vector by default becomes a linearly dependent set. Okay, now number 3. If S is linearly independent, I'm going to use the shorthand Li for that. If S is linearly independent, then every subset of S is also linearly independent, right? This in fact follows automatically from number 1, because if any subset is linearly dependent, then it cannot S cannot be linearly independent, right? So S linearly independent means every subset of S is also linearly independent. And number 4 is the converse of this, which says that S is linearly independent if and only if every non-empty subset, non-empty, in fact finite, yeah? I can add finite also. Non-empty finite subset of S is linearly independent. Think about this. Once again, this also follows automatically, immediately from the definition. So that's how we have this linear dependence idea. Okay, I'll give you some immediate attention problems where you will be asked to check for linear independence and linear dependence, but those will come very soon once we finish this module. But let us proceed to the next idea, next important idea, which is actually dependent on this definition of linear independence, which is the following. First, let me use this term. Do I need this? Well, actually, it's important for us. But let me first define this particular term, namely once again about span. I'm going to use this word G now. G. Suppose G is a subset of V. V is once again a vector space over a field F. So let G be a subset, just an ordinary subset. If G spans all of V, then G is called a generating set. Yeah. Generating set of the vector space V. Cool, no? That's it. That's the definition of generating set. Now comes the big definition, the big reveal. Namely, so this is a definition of basis. I'm sure you have heard this term before multiple times. Basis functions, basis vectors, this, that, but what they really are. Okay. A set G, which is a subset of V, hang on, my Apple Pencil has run out of battery. Just hang on a second. Yeah, so you're back. So I was saying that a set G, which is a subset of V, it's not a subspace, yeah, remember, so it's a subset and possibly infinite, doesn't have to be finite. A set G is a subset of V, is said to be a basis of the vector space V if G is span of G is all of V. That means G is a generating set first, and remember, and G is linearly independent. So a linearly independent generating set is a basis. Linearly independent generating set is a basis. That's what it means. Yeah. Let us look at some very quick examples of basis. Okay. First of all, f to the n. Now, by f to the n, we actually mean f to the n cross 1. So these are columns of numbers, right? So also f to the power n cross 1. Here, I say E1, which is 1 0 0 all zeros, E2 0 1 0 all zeros, then E3, which is, so these are all by definition, yeah, by definition, 0 0 1 0 and all zeros, right? And so on up to En, which happens to be 0 0 0 0 finally 1. Yeah, this is E1 up to En. This set is a basis for f to the n. Yeah, why is that so? Because a typical element, say alpha 1 dot 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 up to alpha n. This is a typical element in Fn where alpha 1 dot 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 up to alpha n, they are elements from F. So this is a typical element in f to the n, right? Of course, this vector, which is alpha 1 dot 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 up to alpha n, can be written as a linear combination alpha 1 E1 plus alpha 2 E2 plus dot 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 up to alpha n En, right? So that's why this is a generating set. So this implies yeah. So this implies E1 dot 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 up to En. This is all of Fn. So indeed, this is a generating set. Now, how do I know that this is linearly independent? Okay. To check linear independence would mean consider this linear combination alpha 1 E1 dot 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 up to alpha n En. And suppose this guy is the zero vector. What is the zero vector? If I expand this, this is nothing but 0, 0, dot, 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 up to 0, right? But this linear combination means this is alpha 1, alpha 2, dot, 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 up to alpha n, and that is equal to 0, 0, dot, 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 up to 0. So this obviously means alpha 1 is 0, alpha 2 is 0, dot, 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 alpha n is also 0. All the coefficients are 0. So the only linear combination that goes to 0 is the trivial linear combination. Remember that no non. So having independence means what? Independence means that no non-trivial linear combination of these vectors can go to 0, which means the only linear combination that can go to 0 is the trivial linear combination. That's it. So we have by assuming that a linear combination goes to 0, I have shown that all the coefficients are 0. So that means the only linear combination that can go to 0 is the trivial linear combination. So therefore, these vectors are linearly independent, right? Very simple. Okay, now so this is one example. So this is example number 1. Example number 2 is, once again, if I have F1 cross n, that is row vectors, then F1 cross n has a basis given by 1 0 0 all zeros, 0 1 0 all zeros, dot 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 0 0 0 and 1. This is a basis for row the row space, yeah, space of rows of the vector space given by the rows of numbers coming from F. You can go ahead and check the space of Fm cross n has a basis of the form of these matrices, matrices such that Aij, this is the matrix that is formed by Aij's, that is A11, A12, and so on, right? The standard understanding, where Okay, so let me write this properly. So this collection is given by vectors like, as I said, matrices which are Aij, where Aij is equal to 0 for all um, okay, Aij is equal to 1 for I equal to L, J is equal to K, and is equal to 0 otherwise, and this must go on for 1 L M and 1 K N. So this is the collection. So let me do this for, so this, see this for a while. Let me do this for a particular case, which will be easier for us to understand. So for example, let me do it for M2 cross 3, right? M2 cross 3 as basis given by the following vectors, the following matrices: 1 0 0 0 0 0. This is one. Then 0 1 0 0 0 0. Then 0 0 1 0 0 0. Then 0 1 0 0 0 0 0. Then 0 0 0 0 1 0. And then 0 0 0 0 0 1. Finally, this is a basis. Yeah, you can tally this with this definition that I have listed out here. Right? Think about this. Right? So, okay. Now, on to this question. I'm sure you may have seen that that over R2, when we talk about basis, of course, E1, E2 is a basis. Yeah, E1 happens to be the X1 axis, E2 happens to be X2 axis. And the span of E1 is X1 axis, span of E2 is the X2 axis. Right? Span of E1, E2 is the whole space. Now, you can also take two other linearly independent vectors, and they will also span R2. In fact, take any two linearly independent vectors that will span R2. Similarly, for R3, take any three linearly independent vectors that will span R3. Yeah? Why is that so? Is this a coincidence about this number? So for R2, two linearly independent vectors will suffice. For R3, three linearly independent vectors will suffice. Is this a coincidence? While you think about this coincidence part, let me give you one more exotic example, which is for the infinite dimensional case. So I did talk about polynomials the other day, and the symbol was fx. Yeah, what does this mean? This contains elements of the form a0 plus a1x plus dot 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 up to anx to the power n. This is a typical element where this a0, a1, these numbers are all coming from the field f. This is a typical polynomial. This is a vector space we have seen in the last lecture. What is its basis? Can we find a basis for this guy? You see, here a basis can be found to be 1, x, x squared, so on. This is an infinite set, but still it's a basis. So this goes to you as an immediate attention problem. Prove that this is a basis for the polynomial, that's the space of polynomials. Show that this is linearly independent and show that every element, every polynomial can be written as a linear combination of these vectors. Okay, so this goes to you as an immediate attention problem. Now, coming back to the question of coincidence, whether it really is a coincidence that R2 needs 2 linearly independent vectors, R3 needs 3 linearly independent vectors, R4 in all likelihood would need 4 linearly independent vectors. Why is that so? Here is this great theorem which will prove, which will finally tell us why this is true. So suppose, so here is the theorem. So let us first state the theorem and then we'll do a proof of that. And then we'll see two quick corollaries of that theorem. Two profound but yet quick corollaries of that theorem. So theorem says that, okay, let V be a vector space over, of course, a field F. Suppose there exists V1, V2, dot, 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 up to Vn, a finite subset of V such that the span of V1 up to Vn is all of V. So this means that we say in words that V admits a finite generating set. So V admits a finite generating set, right? Then any collection of vectors from V containing more than n vectors must be linearly dependent. This is the statement. Notice that V1 up to Vn need not be a basis. I'm not saying V1 up to Vn are linearly independent. I'm just saying that it's a generating set, but it's a finite generating set and has exactly n number of vectors. So I know that the vector space is generated by n linearly n vectors. Whether linearly independent or not is not my concern at all. I just know that it's generated by n vectors. Then any set that contains more than n number of vectors can never be linearly independent. Yeah, strange, no? But now let's see why should this be true. The proof once again is fascinating. Although I say fascinating, but what it really is basic bookkeeping. It's basic keeping of the indices, writing the indices properly. Yeah, and using some very basic facts about the things that we have learned about abstract vector spaces. Okay, now what are these basic facts and what is this bookkeeping technique, right? First thing, so let W1, W2, dot 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 up to Wm, right? Yeah, Wm be a collection of vectors in the given vector space. Yeah, with m strictly bigger than n. Okay. In fact, I think it would be better for us. It would be, although it doesn't really matter. It's a very small issue, but I think it would be better for us if we consider this as m. More than m vectors, and this we consider as n. Yeah. Because that will be more aesthetical, not aesthetically, kind of psychologically, this will be, this we take as n. We'll see the reason why I'm doing this small adjustment very soon. N is strictly bigger than M. So I have M, the generating set has M vectors. And I'm taking N vectors, W1 up to Wn. Yeah, so it is enough to show that these are arbitrary vectors. Yeah, I have not made any specific choice about these vectors. So these are arbitrary vectors. So it is enough to show that this set W1 up to Wn is linearly dependent, right? That's what that will prove the theorem. Yeah. Now, okay. So listen, what do we know? We know that W1 up to Wn are arbitrary vectors, and V1 up to Vm are generators, which means for since V1 up to Vm spans all of V, for W1 there exists A11, A21, A31 dot up to AM1, all are coming from the field such that W1 is equal to A11 V1 plus A21 V2 plus dot up to AM1 Vm, right? A linear combination. W1 must be a linear combination because W1 is a vector in V, and every vector in V is a linear combination of V1 up to Vm. This is one particular linear combination. Similarly, likewise, W2 must be equal to A1 to V1 plus A2 to V2 plus dot plus AM to Vm. Similarly, up to Wn, which is equal to A1 N V1 plus A2N V2 plus dot plus AMN Vm. Yeah, so we have these linear combinations for these W's. Now let x1 W1 plus x2 W2 plus dot up to xn Wn be a linear combination of W1 up to Wn. Right? I'm going to write this as a linear combination of vectors in V. So that's what we're going to do. So let us do this for this thing. X1 W1 plus X2 W2 plus dot up to Xn Wn. Suppose this is equal to 0. Yeah, we have to show that. Suppose this is equal to 0, to show that X1, X2, to show that okay, to show that there exists x1 dot up to xn in F, not all zeros, such that, okay, let me write it this way, such that okay, sorry. Let me write it. No big deal. I was trying to copy paste to show that not all zeros, such that x1 W1 plus dot up to xn Wn is equal to 0. That will prove that W1 up to Wn are linearly dependent. because a non-trivial linear combination, not all zeros, right? Non-trivial linear combination goes to 0. Okay, so suppose we have this. This is equivalent to what? This is equivalent to x1. Now this I'm going to write as, remember this linear combination W1 is A11 V1, A11 V1 plus A21 V2 plus dot 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 up to A M1 VM, right? Plus x2 into A12 V1 plus A22 V2 plus dot 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 plus A M2 VM plus dot 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 xn A1n V1 plus A2n V2 plus dot 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 up to AMN VM. This ought to be equal to 0. I have just replaced W1 up to Wn, substituted for them by the linear combinations that I have for W1 up to Wn in terms of V1 up to Vn. Yeah, of course, this then implies is equivalent to, now I'm going to write these V1s together. What does that give me? That gives me the following. Summation, notice carefully, I have A11 x1 plus A12 x2, right? Which then, so let me not use this summation term, let me use it this way. A11 x1 plus A12 x2 plus dot 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 A1n xn times V1. This is rearrangement, taking all the V1s together. I will take now A21 x1 plus A22 x2 plus dot 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 up to A2n xn. This multiplies V2 plus this will continue. This will give me finally AM1 x1 plus AM2 x2 plus dot 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 AMN xn times VM. This ought to be equal to 0. I'm going to give these guys some name, these linear combinations. So notice the first one is A11 x1 plus A12 x2. So define x2 plus dot 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 up to A1n xn equals y1. The second one is, A21 x1 plus A22 x2 plus dot 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 up to A2n xn equals y2. Finally, I'll have AM1 x1 plus AM2 x2 plus dot 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 up to AMN xn. This must be ym. So if I do these definitions, then then this equation, which let me call 1, then equation 1 is equivalent to y1 v1 plus dot 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 up to ym vm equal to 0, right? Yeah. Now let us look at these y equations one more time, and lo behold that I can write this y equation in this form. Once I write this form, this will be obvious to you. Why should the theorem be true? Let me write the equations for y1, all of them together in a matrix form. A11, A12, dot dot dot, A1n, A21, A22, A2n, AM1, AM2, AMN. This is the matrix. This multiplies x1, x2, dot 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 up to xn. This multiplies, that is equal to y1, y2 to ym. Yeah. Suppose the right hand side is all zeros. If the right hand side is 0, then this linear combination also is the trivial linear combination, so it will go to 0, right? Now notice the thing. What did we start with? I start with this linear combination of W's. That is this one, right? I wanted to find out whether there are non-zero x's, x's such that not all of them are zero, such that the linear combination, that is this one, this goes to zero, right? Now, remember, I want x1 up to xn, not all of them zero, such that this linear combination goes to zero. But I say that is equivalent to say that this matrix is, let me define it as A, and this is X, of course. So there exists a non-trivial linear combination of W1 dot 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 up to Wn that equals 0 if there exists x not equal to 0, a non-zero vector in Fn such that Ax equal to 0. So if I can find out a non-trivial solution of this homogeneous system of equations, system of linear equations, that will imply that there is a non-trivial linear combination of W1 up to Wn that is equal to 0, right? So then it's enough to show that, enough to argue that Ax equal to 0 admits non-trivial solution. But this is true, no? Why? Come back. What is the size of this matrix A? M cross N. Yeah? How many variables? N. How many equations? M. What is the condition that we have imposed on this system? N is bigger than M. So by our star theorem back in lecture number 3, if I'm not mistaken, lecture number 4, whatever, star theorem. Go back and check the star theorem, which says that if there are less number of equations, more number of variables, then a homogeneous system of equations will always admit non-trivial solutions. So, but this is true. This is true by earlier theorem because M is strictly less than N. So this completes the proof. Yeah, now see, I will write 2 corollaries of this result. 2 quick important corollaries. Corollary number 1. Suppose V admits a finite generating set like before, like in this statement of the theorem, then every basis must contain exactly the same number of vectors. I'll not do the proof. You think about it because this immediately follows from the theorem. So let me just do a sketch of the proof. Let me just say it. You think about this. This is there in the book, so you should read the book and you should know it, more formally. But let me give you the sketch of the proof. Okay, V admits a finite generating set. So by the theorem, so suppose that number is some M or whatever, some N. Some M. Yeah, M is a finite generating set. Any collection of vectors that is more than any collection that is more than M cannot be linearly independent, right? So which means if there is a basis, then that basis must have finitely many elements, right? Yeah, because the generating set is finite. So any set having more than that number of elements cannot be linearly independent, but basis has to be linearly independent. So basis has to be finite. Okay, now suppose there is a finite basis for one basis. Say we call that basis as B1. B1 has say n1 number of elements. And suppose there is another basis B2. B2 has n2 number of elements. Now B1 n1 because B1 is a basis, it's a generating set. So we have a generating set that contains n1 number of elements. On the other hand, B2 is also a basis, so it's linearly independent, right? Which means by the theorem, n2 must be less than or equal to n1, right? Secondly, because B2 is a basis, so B2 is a generating set which has n2 number of elements, and B1 is a basis, so linearly independent, which has n1 number of elements. So n1 must be less than or equal to n2. So I have n2 less than or equal to n1, n1 less than or equal to n2. That means this has to be n1 must be equal to n2. Let me do that proof anyway. Proof. Let by theorem every basis must be finite. Okay. My laptop battery is draining. Just hang on a second. Yeah, we are back again. Right. So a basis must be finite. So now let B1 be a basis with number of elements in B1 equal to n1, and B2 be another basis with number of elements in it equal to n2. Since B1 is equal to V by, and B2 is linearly independent because it's a basis, by theorem n2 must be less than or equal to n1, because if n2 is more than n1, then it cannot be linearly independent by theorem. Further, since B2 spans V and B1 is linearly independent by, once again, by the theorem, n1 must be less than or equal to n2, which implies n1 must be equal to n2. That's it. Corollary number 2. Oh, but before we come to corollary 2, corollary 1 actually allows us to give a definition, a great definition. Definition of dimension. We have been saying this term dimension so often, but we have never formally defined it so far. This is how, here is the definition. Okay, so let V admit a finite basis, then basis say B, then dimension of V denoted like this is defined to be the cardinality of this set of this basis B. See, this is well defined. Although I'm taking only one basis, in reality there could be multiple bases, right? There could be infinitely many bases, but each of those bases will because it is a finite, because there is one finite basis, each of the other bases also will have exactly the same number of elements, exactly the same number of elements. That's what corollary 1 says. And therefore, no matter which basis I took, this number will always be the same. And that number is called the dimension of the vector space, right? This is the definition of dimension, which means dimension 2 means there is a basis of size 2, and every other basis will also have exactly size 2, not more than 2, not less than 2. The dimension is n, that means there is a basis with n number of elements, and every other basis will also have exactly n number of elements, not more than that, not less than that. Yeah, that brings us to our second corollary, which is corollary number 2. It says that let V be a vector space whose dimension is equal to n. Then number 1, any collection with more than n vectors must be linearly dependent. Any collection with less than n vectors cannot span V. First one is obvious. Second one says that if there are less number of vectors, then it cannot span V. It can be linearly independent, but it cannot span V, because if it is linearly independent and it also spans V, that contradicts the fact that the dimension is n, because we know that in that case it would be a basis. Yeah, and if it's a basis, its size must be exactly equal to n. Yeah. So think about this. I'm not doing the proof. Okay. Yeah. So let us finish this module here. These are the companions. This is the companion note. These are the problems that you're supposed to solve together with the ones that I've mentioned during the lecture. Prove that if two vectors in an abstract vector space are linearly dependent, then one of them must be a scalar multiple of the other. Very simple. Then a concrete problem where I have given some vectors. I've asked you to check whether they're linearly independent or not. Will turn out to be dependent. Yeah, I think. Then find out a basis for this span, for the span of these vectors. Then two homeworks, find out a basis for all symmetric 4x4 matrices with real entries as a vector space over R. And then let V be a vector space over a subfield F of the complex numbers. Suppose x, y, z are linearly independent vectors in V. Prove that x plus y, y plus z, and z plus x are also linearly independent. Then homework number 3, let A in our be a matrix, a square matrix. Then prove that the column span of A is Rn if and only if A is invertible. Repeat the same for row span. By the way, I have not defined row span and column span yet, but it's kind of understandable that the name itself is quite self-explanatory. Column span means column span of A, where A is a square matrix, any matrix of any size in fact, is by definition the span of the column vectors of A, and row span of A similarly the span of the row vectors of A. Right? So do these problems and think about everything that I've said. I've said a lot of things today in this module. So think about them. And once you're done with that, let's meet for the second module of this lecture. Okay, till then, bye-bye.